Hello and welcome to a new DIY Engineers video. In this video I'll be walking you through a new project I did for a rotating LiDAR scanner. In the video I'll walk you through the 3D model, printed circuit board design, the assembly of the LiDAR scanner, putting together the printed circuit board and the components, Arduino programming, and of course we'll test it. We'll test it via low speed testing as well as a high speed scenario. So let's go ahead and get started. So here we have a 3D model of the LiDAR sensor. You can see the full assembly. Let's focus first on the actual sensor. We have here the TF Luna that I showed in a previous video. Then we have here a 3D printed part that basically will attach the sensor to it, and the wires coming out of the bottom of the sensor will go through this hole here, exit at the bottom, and then there's 3D printed part that's essentially a gear slash attachment for the sensor. Will spin about this axis formed by this plastic support from this side of the 3D printed part. That also has a hole to enable the cables from the sensor to come out of this hole. Sorry, out of the hole really coming from here. So this one. And then this essentially is a component that is used to allow for wires to rotate on one end and not on the other, and I'll show that in detail. And that will get attached on these three holes, and the cables will come out of here. So then we also have 3D printed gear, which will attach to the shaft of the motor. This is a stepper motor, which attaches to this bracket. So once you have that full assembly between this wire management component, the component that grabs the sensor, and the gear, and the stepper motor, all that will essentially then be attached to this part, which attaches to this housing via these holes here. We also have the top cover that will cover all the top components and allow the sensor to exit through the top. We have this hole here, which essentially is for this part of the printed circuit board so that you can connect power to it. And then we have the bottom plate where printed circuit board rests on top of, and you can also close it at the bottom with this parts here. And then you use screws that go here. So that is the actual component. And of course, we have our microcontroller, which is a NodeMCU on this one. And then we have similar components that we have used for our previous stepper motor videos, which is a A4988. Stepper motor driver, as well as some components to allow for grabbing the cables and the typical, resistors and whatnot components that go into your printed circuit board. So then let me collapse all this, and here you have it. Here's how it looks. Now here we have the schematics of our printed circuit board. So here we have the header where we're going to connect the NodeMCU, the left and right end. Here where we're going to connect the TF Luna LiDAR sensor. Here's where the A4988 gets connected. And then here's where we connect the motor, the stepper motor. So then on that, we have here's where we connect power. This is the typical jack that you will see in the video. Provide 12 volts. We have a couple of capacitors to smoothen the load going into the motor, and then just smoothen really the load coming from the 12 volts in general. This will convert from 12 volts to 5 volts, and we have a capacitor too that goes with it. And then here we have general connections for our LiDAR sensor per the diagram shown in the previous video showing you what to connect to what. So we have configuration and ground connect together to the ground on the NodeMCU, mainly because we want to use it in I2C mode. We have 5 volts connected to the 5 volts that we talked about here. This is 5 volts out of this converter. We also have those 5 volts going into VN onto our NodeMCU. We have SCL and SDA out of the LiDAR sensor going into our NodeMCU I2C pins. And then we have a few here going into our stepper motor, as I've shown before previously on how to control it. And reference those videos on stepper motor and LiDAR sensor if needed. This shows the routing of how all those connections are actually made into the printed circuit board. Here's the connections of the LiDAR sensor, the connections to our stepper motors. Here we would have our stepper motor driver Here's the NodeMCU. This is our converter. Here's where we actually connect the 12 volts. And here we have a few capacitors. And this is the top layer. And if you want to see the bottom layer, that's what it will look like. So red lines are top layer, blue lines are bottom layer. And both the circuit schematics as well as this view of our printed circuit board are made with ECEDA, which I've shown also how to use in a brief video that I've shown previously in this channel. Now, this is the wire management component that I previously mentioned. It's actually called an electrical slip ring, and I'll leave a link in the description. Here's the part that I previously shown the 3D model. And here's where the stepper motor goes. I'll go ahead and add the screws. Crop a few sections out of this to go a little bit quicker. We'll basically fix it with 4 screws, 1 in each hole that the motor already comes with. So next, I'll use 4 screws to attach the electrical slip ring to this 3D printed part. And I've made the 3D printed part having embedded nuts such that I can actually screw to it. So it's not like the part is threaded. I just stopped the print, added a nut, built it in, and continue printing. So that way I can, firmly attach these type of components. And I'll also show you how I do the same in another part. So now that I have it fully secured, you can see that one side is fixed and the other one I can rotate without the part on my other hand rotating at all. So that will enable us to rotate the LiDAR sensor without rotating the connections that will be connected to our printed circuit board. So next we'll go ahead and put the driving gear on top of the motor. You can see it pretty close. There's a tiny gap and it rotates pretty smoothly. And next we'll put the gear / part that attaches to our LiDAR. We'll slip the cables through and there you have it. We can rotate the green gear, the driving gear, which it costs us pretty much to rotate the sensor gear. And you can see how the top cables rotate without the bottom ones coming out of the slip ring rotating at all. So now I just wanted to show you a little bit of the 3D printing. You can see that I have a similar method here. I have some nuts into the housing that we'll use to host our components. Here's a little bit more advanced into the print, and then later I'm showing you how it's fully completed. Alright, our 3D print is finally complete. You can see there the supports helped us build those lateral supports there will be for the motor. So now let's go ahead and take it off. So now I'll go ahead and remove the 3D printed support structure that the printer prints to enable supporting some of those overhanging features. So I received my printed circuit board, my surface mounted components, and I went ahead and added some solder paste. I'm now go ahead and cook them in a mini oven so that I can adhere or mount the surface mounting components into my printed circuit boards. And then after that I'll go and put the other components that go through the through holes. So let's go ahead. Alright, so let's go ahead and put it in. Now we wait. And as we can see, it's already melted, so we're good to go. Alright, so here we have our printed circuit board with the surface mounted components already added. 1, 2, 3, and 4. And now we're going to go ahead and add the through wall components. So let's do that. So here we have it. We have all our SMT as well as through wall components installed and ready to go. We can now begin the assembly process of some of our components. And basically, I'm going to be attaching our rotating component assembly to the main shell or housing. Although before I get too far, I'm going to have to cut the cables out of that electrical slip ring and solder the main connection that goes to the LiDAR sensor. After that, I went ahead and resumed the assembly process by really first going and connecting or attaching the shell to the top dome, because it's easier to access our components that way. And then I can go ahead and proceed to route my USB cable through the lid and then attach it to the bottom. And now we have our full assembly ready to go. We can see our LiDAR sensor is spinning. Let's take a closer look. And that right there means we're ready for coding. So let's go ahead and do that. Alright, so let's go ahead and take a look at our Arduino code. We start by including Arduino, wire, TFL I2C for TF Luna I2C library, and Axel Stepper. This is one that I haven't used before. So go ahead, and if you don't have this library, go ahead and install it. That's simply by going to Sketch, Include Library, Manage Library, and then just wait for it to load. See here at the bottom. There you go, and then just type it up, Axel Step, and it's this one by Patrick Wasp. So if you don't have it, install it. Here we initialize our TFL I2C. We define inputs that are relevant to the stepper motor. We define the stepper motor interface. Pick one. Then we define stepper motor. We define some constants for stepper motor. Now you might have seen a previous video where I use the exact same motor with a steps per revolution of 200. So you might wonder why here I have some odd number that is not even a whole number or integer, and that has to do with our gear ratio. So I showed earlier the gears used for this project, and since I really care about the rotations of my sensor, I have to take into account that a full rotation of the gear being driven by the motor does not equal a full rotation of the gear in which the sensor is mounted. So I use this different factor, basically taking the 200 and multiply by the reduction factor from the gear ratio to get to my net steps per revolution. So that's what that is. Here you can define the speed at which you want to run. I really tested different ones that I'll show later. Just look into your motor if you're replicating this video to make sure that you're within the maximum limits of your motor. Anyway, so here are some other LiDAR sensor inputs. I also went ahead and defined the constant pi because I'm going to use it later on. And then we'll go into the setup where we define some pin modes. Same thing for the stepper motor. We'll begin wire and we set some parameters for the stepper. And then we'll go into the main loop where we set high on the sleep button. That way it's always not sleeping. You can go ahead and put a low if you want to put your motor to sleep when some logic happens. And then here we have an if statement that basically is used for tracking of the position of our stepper motor. So if n, which is basically the steps that we're tracking, is greater than the steps per revolution, then go ahead and perform a division and get the remainder. By the way, this would have been the same number that I got here. Yep. So the remainder, and of course I'm putting into an integer because this is required for the operation of that division, but we'll take the remainder and that remainder will then become n. and we'll start again that count. And then of course the angle is used by taking n divided by the steps per revolution, because n is the count of steps, and multiplying by 360, which is 360 degrees. This is what's used to run the stepper motor at the speed previously defined here as stepper set speed. And then steps per sec is what we defined here earlier as steps per second. And then this will simply go ahead and call position 2 equals the current position of the stepper, which is really how we're defining n, which is just tracking the steps of the current stepper motor, which goes beyond the 116.95 steps per revolution. So it keeps going up. That's why I divide, and the remainder is what goes into n, so that I can use it properly in my angle equation. And then here, if we get data from the LiDAR sensor, we went ahead and print to the serial monitor the angle, the distance, and then n, which is equal to the number of steps as we talked before. Now, this will all be used along with processing IDE, which I actually have used in a previous code, in a previous example. If you don't have it, go ahead and install it. On processing IDE is the name of the software, and it's used in this example to plot. So we'll be sending data through the serial monitor and collecting it in that other software, and then extracting the data from, being communicated via serial monitor and using it to plot. So now let me show you the code for that. All right, so now I'm in processing IDE, and this is the code that you will use. We start by defining a vector, which will basically be used to collect all the positions from angle, distance, and n from the Arduino code and store them in an array of vectors. This can get slightly complicated, so I'm not gonna go into too much detail. You can copy and paste the code, but you can see here how we're referencing the data from the serial monitor. You need to make sure, if you copy and paste my code, you should be fine, but if it's key to make sure that you're using the same setting in the serial monitor. So here we have the 115200, same as what we had in the Arduino code under serial begin. Here we're still defining the vector and adding a few points. And then here we have that basically if there's data coming from the serial monitor, we want to go ahead and define R as the first variable coming out of the serial monitor, which would have been the angle in radians. That's why we went ahead and in the Arduino code multiply the angle by pi over 180. Next, we'll have the second component, which basically will be the distance. And then finally, we have n, which is n from the Arduino code. We'll also then calculate x and y, which is just f, which is a magnification factor that you can change here to make the information or the graph bigger or smaller, or the circle being plotted, or whatever shape is being defined by the LiDAR or measured by the LiDAR. You can make it bigger or smaller by increasing or decreasing this number. Multiply that times sine of the angle. Again, the angle is this variable that we had here, times r, which is the distance, plus 50, and that 50 is just based on this 1000. So if you wanted to, move it around, make sure to update this, as well as this. Then we just change the background to 0, which is just going to make the background black. And here's where we do some plotting. We're basically going to be plotting the shape as well as the circle so that you can see the current data point being plotted. Just wanted to provide a brief explanation before you see it running. If you want to copy this code, just go to DIY Engineers. I'll have the link in the description where you will be able to copy and paste it. So now let's go ahead and test some scenarios so that you can see them plotted. So here we can see our LiDAR sensor assembly being tested. Here I'm rotating at a slow speed so you can get the idea of how it's operating. You can see that as the LiDAR sensor is rotating, the screen shows the shape that it's detecting as it rotates. Also, we have a red dot on the screen which represents the point being measured. I will now proceed to put some obstacles that as red dot passes through them, which is essentially the LiDAR sensor measuring them or sensing them, we can see how these are drawn on the chart through processing IDE. If I remove it, then it goes back to the original shape. And I put it back, and it comes up So you can see how we're basically using this rotating LiDAR sensor to map the area around it. Obviously, if I rotated this quicker, we would have a faster response in terms of how soon after I remove the object does it realize that the object has been removed, or how quickly is the image, let's call it, or the map updating. But you can get the idea that basically we have the shape being mapped, all the walls as well as the obstacles are being detected, and the red dot represents what's being measured. And now you can see the sensor rotating at a much faster speed and detecting the objects a lot quicker after they're placed or moved. This concludes the video. I hope you liked it. If you did, give us a thumbs up and subscribe. See you in the next one, and thanks for watching. Bye.